Hi folks, welcome to part 3 of the second optimization lesson. So this question here is similar to the salt shaker problem we would have solved, sort of a very common industrial design problem. So we're trying to design a jewelry box, square-based rectangular prism. So notice here, square-based, that's made up of two types of wood. And so the costs for the different types of wood are different. And they want to determine the dimensions that will minimize the cost of the wood. Now, this is where you have to be careful because, back in grade 9, you would have seen that in some circumstances, the optimal rectangular prism is the cube. Okay, but here notice that there's this constraint that the different parts of the box cost different prices. So I wouldn't assume that I'm definitely going to end up with a cube as my final answer. All right, so again, in order to set this up, as usual, anytime it's something geometric, I'm going to draw myself a diagram. Okay, so I've got my rectangular prism here. Okay, but my base is a square. Okay. So this side length and that side length are the same. So I'll call these X. Okay. And then the height of my box, I'll call it Y. Okay. You can use whatever variables you like. All right. And what I want to do is I want to minimize the cost of the wood. So I need to figure out a way to represent the cost. All right. And we said, we see that the top and bottom cost $20 per meter squared. So if I find the area of each of the top and bottom, I can just multiply that by 20 because whatever the area is in meters squared, I just multiply that by 20. Okay. So I have 20 times, well, the areas of the base and top portion are going to be the same. So it's just 2 times the area of the base. Okay. And then the sides cost $30 per meter squared. So this is going to be $30 times the area of the sides. And the sides, well, are going to be the same all around because X times Y is going to be the area of each of the 4 side portions. So 30 times 4 times the area of the side. All right. So now let's use our variables to determine all of these. So cost is going to be, well, 20 times the area of the base is just x squared. Okay, so 20 times 2x squared. And then here 30 times 4 times the area of the side is just going to be x times y. All right, so let's just clean this up here. So we have the cost is given by 40x squared plus 120 times xy. All right, and yet again, that familiar issue is that the cost is given in terms of these 2 variables. Okay, so we're going to have to find a way to write this in terms of 1 variable. But notice how we haven't used another constraint that was given, as they told us that the volume of the box has to be 4,000 centimeters cubed. Okay, so hopefully this will help us find a way to write this in terms of 1 variable. So we know that the volume of a rectangular prism is just going to be length times width times height. In other words, length times width is just going to be x squared times height y. So that's equal to x squared y. And they give us the volume. So it looks like we'll be able to write one of these variables in terms of the other. Now, this is where you have to be careful. So hopefully you noticed that the volume is given in terms of centimeters cubed, but the areas are given in terms of meters squared. Okay, so I need to either write everything in terms of centimeters cubed or everything in terms of meters squared. Okay, so since I already have these costs, these 2 costs given in terms of meters squared, I think I'm going to work in meters instead of in centimeters. So that means that I have to convert 4,000 centimeters cubed into meters cubed. Okay. Now this is where, I'll kind of do this here. I'll draw myself a little diagram. If I've got sort of, 1 cubic meter, okay, if this is 1 cubic meter, all right, I have to think of this as 100 centimeters, okay? So that means each of these dimensions is 100 centimeters, okay? So now the question is am I going to be dividing 4,000 by 100 cubed, because I've got 3 dimensions, or am I going to be multiplying this by 100 cubed? So we can figure that out, or you can just remember a little trick, okay? As I'm going from centimeters cubed to meters cubed, is my number going to be getting smaller, or is it going to be getting larger, okay? And definitely, when I'm going from centimeters cubed to meters cubed, my actual number should be getting smaller. So 4,000 centimeters cubed, okay, is just going to be equal to, well, I'm just going to take my 4,000 and divide it by 100 cubed, okay, 100 centimeters for each dimension. Okay, so that's going to be equal to, okay, and I'm just going to use my calculator for this to make sure I don't make any silly mistakes. So 4,000 divided by 100 cubed, okay, and that's 0.004. Probably could have done that in my head, but didn't want to make any silly mistakes. 0.004 meters cubed, okay? But now what does that allow me to do? I now know that my volume, which is 0.004, is equal to x squared y. And so that means I can either write y in terms of x or x in terms of y. Okay, and I'm going to choose to write y in terms of x, because if I isolate x, I'm going to have to end up with a square root at a certain point, because here I have x squared, whereas here I just have x, and I'd like to avoid ending up with a square root in my equation if I can. So I'm going to write y as 0.004 over x squared. And so now that means I can input that into my equation. So I've got 40x squared plus 120 times x. Well, wherever I see y, I'm just going to replace that by 0.004 over x squared. Okay, I notice here that the x in the numerator reduces with one of the x's in the denominator. And let's calculate 120 times 0.004, and that gives me 0.48. Okay, so we have that the cost is given by 40x squared plus 0.48 divided by x. All right, so there's my model, and the only thing I have to do now is determine what domain I'm working on. Okay, well again, x is a measure of length, so it definitely has to be greater than 0. And there's no real upper bound here, because I could just have, a very, very wide length with a very, very small height. Okay, so really the only condition here is that x has to be greater than 0. All right, and again, I see I do not have a closed interval here, so I'm going to have to justify any extremum. Okay, so let's go. Now we can do this. We can go to our calculus portion. So derivative of the cost with respect to the variable x is given by, well, derivative of x squared is 2x, so this is going to be 80x, okay? And again, I'm going to think of this as x to the negative 1, so it's going to be plus 0.48 times negative 1 times x to the negative 2, all right? And so here we have and we want to determine when the derivative is equal to 0. So we have 80x minus 0.48 divided by x squared. Okay, and best way to solve this, again, I've got a rational equation, and what was our trick for solving rational equations is just get rid of the denominators altogether. So I'm going to multiply both sides of this equation by x squared, so that's just going to be 0, since 0 times x squared is still 0. And so here I'm going to have 80x cubed minus 0.48, and now I can solve for x. So x is just going to be equal to, well, I'm going to have 0.48 divided by 80, all right? And then I'm going to take the cube root, and that's going to be my single critical value here. Okay, so that's approximately equal to, let's put that in here. So we've got 0.48 divided by 80. All right, and now we're going to take that to the exponent of 1/3. and that gives me 0.182. I guess I'll keep 3 decimal places, 0.182. All right, now this is my only critical point. All right, so I have to hope that this does give me an absolute minimum on my domain. So remember that my domain starts at 0 and can go on indefinitely. So let's put 0.182. All right, and now we'll just pick something to the left and right. So let's say here we pick 0.1, and then on this side we can just pick 1. Okay, so let's go to my derivative, and I'll take this simplified form here. And so let's do this as carefully as we can, make sure we don't make any silly mistakes. So we have 80 times 0.1, okay, and then minus 0.48 divided by, what is that? 0.1 squared. All right, and we've got something negative. And then let's stick in x equals 1. Well, that's just going to be 80 minus 0.48. So clearly that's going to be positive. All right, so let's see what we have. Well, we definitely have a local minimum at 0.182 because I'm going from negative to positive at my critical number. But I see that from 0 to 0.82, this is always decreasing. And then beyond 0.182, this function is always increasing. Okay, so it actually turns out that on my domain, 0.182 is in fact an absolute minimum. Okay, so it looks like we found the x value that gives us our minimum. Okay, let's go back now to the question and see what they're actually asking me for. Okay, so here it turns out they're asking for the dimensions that will minimize the cost. Okay, they didn't actually ask me for the minimum cost. So since I'm looking for the dimensions, well, my dimensions were just given by x and y. So one of my dimensions would just be 0.182. Okay, so the x dimension is 0.182. Now remember, we put everything in terms of meters. And now for my y value, well, remember what we did is we solved for y, so that's just going to be 0.004 divided by 0.182 squared. All right, so let's put that in our calculator. So what do we have? 0.004 divided by 0.182 squared, and that's equal to 0.12, or 0.121, I suppose. Okay, so y is equal to 0.121 meters. Okay, so that means that the dimensions of my box are a base of 0.182 by 0.182, and then with a height of 0.121. And notice here that this is not a cube. Okay, so this one is significantly larger than that one there. All right, so even though in the past you may have found that in other circumstances the cube is the optimal rectangular prism, not in this scenario where the top and bottom costs less than the side lengths. All right, so let's just do a recap here. Step number 1, use our diagram to come up with an equation for the cost of this jewelry box. All right. From there, use the constraint given by the volume to write one variable in terms of the other so that we can write our cost in terms of a single variable, determine our domain, apply our calculus methods, and justify that we came up with an absolute minimum. And then from there, we answered the question that was posed, which was the dimensions of the box. All right, that's it for this one.